Okay, so in this case, we have a few examples. And what are they asking for? So the question that you asked for is question 6. And in question 6, they're saying we have two lines, L1 and L2, and the two lines are said to be orthogonal. Now, what does it mean to be orthogonal? Well, if two lines are said to be orthogonal, it means that the two lines are perpendicular to each other. Think about it as if it was orthonormal something. So here, it means that our two lines are perpendicular to each other, meaning if this is one line, then the other line would perhaps be something like this. So they make a 90-degree angle when they intersect. Now, the question is asking us to find what R will be, given that we have that setup. Well, if two lines are perpendicular, what does it imply? Let's get our two lines. We have L1, the first line. This is x minus 3 over 2. So here they're giving us the symmetric equations for that line. This is plus 1 over 4. And then the last part is z minus 2 over minus 1. See, from here, we can come up with the vector equation of this line. And the vector equation would be x, comma y, comma z. And then this is equal to, so we know how it goes. So we have these, we just change signs. So this is going to be plus 3, and then minus 1, and then plus 2. This is going to be a point on the line. And then the last part, which is here, we don't have the parameter. We can assign a parameter ourselves. So let's use t for this one. So this is going to be parameter t, and then the denominators will be what will fill this position. So we're going to have 2, and then 4, and then minus 1. Here, we just get them as they are. We don't change sign. So this is our line 1. Next up, line 2. What are they saying about line 2? So for the second line, again, they're giving us the symmetric equations. So you have x minus 3 over r, x minus 3 over r. Then this is equal to, we have y plus 1 over minus 2, y plus 1 over minus 2. Then this is equal to, we have z minus 2 over 2. That is z minus 2 over 2. We can also write this in vector form. Again, this is x, y, and z. So a point on the line, again, we'll just swap these, change their signs, I mean. So this becomes, that is minus 3, it will become positive 3. That is plus 1, it becomes minus 1. That is minus 2, it becomes plus 2. So no need for me to write plus 2 there, just write 2. Then the next thing here is we choose a parameter. For this line, we use the parameter to be n. And then what are we going to have there? So for the vector in the direction of this line, the first, it's just the denominators there. So this is r, and then we have minus 2, and then we have, this is going to be 2, positive 2. Now, let's start with the question here. If the two lines were parallel to each other, because we have orthogonal, meaning perpendicular, then we also have parallel. So if they are parallel. Now, if the two lines are parallel, what do we expect? We expect that their direction vectors will be the same, meaning this part here and this part here will be expected to be the same. So if the question said, find r, given that line 1 and line 2 are parallel to each other, would have just seen that, okay, we just have to equate these. Most likely, we would have seen that this would have been the same as this would have been the same as this, and then would conclude that r would have to be the same as that one there. That is, if the two lines were to be given such that they are parallel to each other. So two parallel lines will have the same direction. But in this case, the lines are not parallel. Instead, they are perpendicular to each other. Well, for two lines to be perpendicular, what does this imply? Well, consider one line to be a line like this, and the other line to be a line like this one. To describe a line, we know to say we need one point on the line, and a vector showing us the direction of the line. So one point like this, and a vector showing us the direction. And we can say for the second one, we have our vector, we can take it as this. And our point, we can take our point to be a point like this. Now, if the two lines are perpendicular to each other, let's take the direction of the first line to be u, and the direction of the second line to be v. Now, these are vectors which are running along the direction of each line, respectively. Now, those are going to be the ones to play a very big part in this question, because we know to say if two vectors are perpendicular to each other, which becomes the case here, the vector u has to be perpendicular to the vector v if the two lines are perpendicular. So if two vectors are perpendicular to each other, what does that tell us about their dot product? Do you remember? The dot product is going to be equals to 0. So if u and v there are perpendicular, then u dot v will have to be equals to 0. So this is the equation that we'll be working out. But what is our u? What is our v? We can take u to be coming from line 1, and u here can be taken as the vector 2i, and then we have, let me write it somewhere I can easily get it. So I can take u to be equal to 2i plus 4j minus k. That is our u. Then we can take v to be coming from line 2. So u becomes ri minus 2j, and then we have plus 2k. Have you seen that? Yeah. So we'll just dot these two and equate them to 0. So you know how dot product goes. I can write first, this is 2i plus 4j minus k. I am getting the dot product with ri minus 2j plus 2k. What is this giving us? It's supposed to give us 0, but let's get the dot product. You know how dot product goes? It's corresponding, meaning the things with I will multiply, giving us 2r there. With j, we have 4 and minus 2, giving us minus 8 there. Then with k, we have minus 1 and 2 there, giving us minus 2. This is what is going to give us 0. So clearly, we have 2r minus 10 is equals to 0. 2r is equals to 10. And finally, r is equals to 10 over 2, or r is equals to 5. Then we're done. Now, if you wanted to work out question 5 here, of course, they're saying that the two lines are parallel. So if they are parallel, what it means is their direction vectors have to be the same. I think I did hint at that earlier on when I was saying this has to be the same as this has to be the same as that, this has to be the same as this, if two lines are parallel. So in this case, the first thing that you'd have to do is transform each line into its vector form if you can't see it from the way they are. But you can still identify the direction vectors even if the lines are given in this form, but it's just easier if you write them in vector form. So let's get each equation in vector form. I'll just get the vector representation of each one. So let's get line 1. We have x, y, and z. In vector form, this will be equal to, it is in parametric form, so the next one is going to be a 1, exactly with the sign. And then for y, what would be the y value there? What'd you get? This one will have to be 0. From here, we'll get 0. Yeah, so from there, we'll get 0. Then the next one is going to be from this parametric equation, we're going to get minus 1. Then next, the vector, the direction vector. So for this part, the parameter they're using is t. So let's get t. And then let's see what we have. Then what comes there from this part, we have minus a. So this is going to be minus a. And then the next part, we have 5t, or just 5. That is going to be 5. And then from the next one there, we have minus 14. This is going to be minus 14 there. So that is the vector equation for line 2. For line 1, I mean. For line 2, again, we have x, y, z. Now remember how this one goes. Since we are given line 2 in symmetric form, and observe that we still have this 2 that is outside there. So you see, that 2 is a little bit tricky, how you treat it from there. So if you're going to make a shortcut, remember how it goes. The variable x does not have a coefficient. It's just x minus something. So where do you think that 2 is coming from? Can you try to guess where the 2 is coming from there?
Assuming 7 is 14 and x is 2.
No. Again, like I was saying, in symmetric form, this x is always like this. The y is like that. The z is like that. They don't have, the coefficient they have is a 1. Do you get my point?
Oh, okay. So it's from the denominator.
Exactly. It's from the denominator. That's what I wanted to hear. So in other words, this part here, it is actually supposed to be x plus 7 over 1 over 2. Same thing here. This is y minus 100 over 5 over 2. But the last one doesn't have the fraction, doesn't have that. It's just what? It's just z plus 19 over minus 7. So this is z is it plus 19? Minus 7, is it? Oh, minus b. That's minus b. Minus b. And this is plus. Okay, that is what we have. Yes, plus 19 minus b. So I hope you've got that. Once we have that in check, we can now easily get the vector equation. Remember how we get the vector equations? The value here changes sign. That is plus 7, we get minus 7. This is minus 100, we get plus 100. No need for the plus. And then we have plus 19, we get minus 19. The parameter we'll pick here, we can go with n. But what will be the values here? Let's see what we get here. So when you look at this, after completing the vector equation for line 2, we want to equate this. We want to say this is the same as this. This is also the same as this. But a key success condition is that the only number that we know, they must be the same. But here we see that 5 is not the same as what it corresponds to. It corresponds to, 5 is trying to correspond with 5 over 2. The two are not the same. You've seen that, right? So we cannot really equate them just as they are. Yeah?
Yeah, so I'm assuming whatever we're going to get for A and B, we're going to have to scale it to the same thing we have for 5, which in this case is 5 over 2. So whatever we're going to get, we're going to have to divide by 2 as well, right?
Yeah, so we're seeing that thing where we probably have to divide whatever comes from here by 2. Or we can scale these vectors. We can scale one either up or down. Do you get that?
Yes.
Yeah. So if I was to divide this one here, if I was to redefine this parameter t to maybe say t is equals to m over 2. Notice that redefining it means that I haven't changed the direction, have I now? I haven't, right? I'm just saying that if it is that long, take it halfway. So it doesn't change the fact that they are still parallel. So what would this mean? It would now mean that I'm changing this parameter from t to like something like m over 2, but the over 2 now comes here. We should make this over 2 as well, right?
Yes.
Yeah. So that now the minus a, so let's get this. So if we were to now relate those, so this would imply that we have minus a over 2 is equals to 1 over 2. And clearly this becomes a is equals to minus 1. Right? Now this works because this is now 5 over 2 and this is also 5 over 2. So the others must match up since they're parallel.
Yes, I do.
Yeah. And when it comes to the second one, for b, it implies that minus b has to be equal to minus 14 over 2. This implies that b has to be equals to what? To 7. Is that okay?
Yes, it is.
Okay.
Yes.
So what I'm saying here is when coming up with the parametric, the vector equation, this part here, you have to see that the denominator in the original question is a minus 1. I wrote it as a positive 1 over 2. This is minus there. Do you see that?
Okay.
So this has to be minus 1 over 2. So meaning that when I bring it here to make the vector equation, this is actually minus 1 over 2. So the minus 1 over 2, that is the only thing. Meaning when we equate minus a over 2 to minus 1 over 2, this comes to ensure that we get a positive 1 for a. So this is now equals to minus 1 over 2, which makes this plus 1. Everything else is still fine. So this is now okay, right?
Yes, it is.
Okay, so this is how we approach that question.